Good morning, everybody. Welcome to Wednesday morning at Chem 1211 with your host, me, Dr. White. Hi, everybody. Let me just remind you, if you haven't already, you should take test number 1 either today or tomorrow. Tomorrow, Thursday, the 20th is the last day you can take test number 1. Otherwise, you get a zero. A zero. You don't want that. I don't want you to get that. So be sure to take test number 1. Now, yesterday we were going through gases, and I'd like to go back and do another 2 gas law problems. And let's do the following. Yes, that's 15 points. I was about to start writing and I realized, oh, his students don't know cursive, most of them. Hang in there, I'm almost done. All right, let's read it. I'll read it for you. A balloon contains oxygen gas, that's what O2 is, oxygen gas, at 31.2 degrees C, 752 torr, with a volume of 4.56 liters. How many grams, G of oxygen, are in the balloon? And let's take a look at this. What are we being asked to find? How many grams O2? What are we given? Well, we're given the temperature is 31.2 degrees C. We're given the pressure, remember torr, millimeters of mercury, atmosphere are units of pressure. And we're given the volume. It says this, and liters are unit of volume. So this is what we're given, and this is what we're trying to find out. Now, wait a second. We're dealing with a gas. And if you notice right here, does the temperature, pressure, or volume change? No. So, also, when you see 15 points, this is the only problem this whole semester. It's that many points. It's PV equal nRT. But wait a second. P is pressure, V is volume, N is moles, R is the universal gas law constant, and T is temperature. That doesn't have any grams. What do I do? Well, think about this. Hopefully you learn that you can go from moles to grams. You go from grams to moles. So if we want to find grams, If we knew the moles of oxygen, we could then calculate in a second step the grams of oxygen. Well, how do we get moles? N is the moles. So, in case you forgot, if you look on your screen, this will be given to you in quiz number 3, important information. I've got to change this file, so we'll say that. But if you notice the ideal gas law, PV equal nRT, and right here, N is the number of moles. You'll also be given 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound is the sum of all atomic weights. So now we know we can solve this problem. What we first have to do, you need 2 steps. First step, you have to find the moles of oxygen. Second step, convert moles of oxygen to grams of oxygen. So we better get to work. Step 1, we want to find moles of oxygen using PV equal nRT. Well, how do we solve for moles N of oxygen N for this equation? We need to get it alone on one side. Oh no, there's R and T in the way. When things are multiplied, remember, anything divided by itself equals the number 1, cancels out. So if I want N alone on one side, what do? I divide by RT. R divided by R is 1, T divided by T is 1, 1 times N is N. But whatever you do to one side, you have to do to the other side of an equation. Now this cancels out, and I'm left with N, which is moles, and that's equal to PV over RT. And I'll rewrite this N equals PV over RT. So at this point, we have to first find what's the pressure, P. Now, if you look at important information, quiz number 3, once I change this, right now it's called test number 3, you'll see pressure has to be in atmospheres. Pressure has to be in atmospheres. We're given it in torr, but you will be given this relationship right here in important information. In the past, students have to memorize this. I'm just asking you to know how to use it. And here, 760 torr equals 1 atmosphere, also equals 760 millimeters of mercury. Excuse me. So to get pressure, did it again. It's Dr. White wants to write in cursive Wednesday. To do this, you start with the pressure, 752 torr. We could convert it. We want to get the atmospheres. And how do you do that? Well, you need a ratio. And how do you find what's on top and bottom of that ratio? Use your good buddy, Your good friend, unit analysis. I love that whistle siren. And whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And I'll write those numbers, well, the units in first. And where do I get a relationship between atmospheres and torr? Well, in case you forgot, you can always look at important information, which I'll change hopefully this weekend. Quiz number 3, 760 torr equals 1 atmosphere. 760 torr equals 1 atmosphere. 1 atmosphere, 760 torr. These are part of a definition, so they're both exact numbers. And now before I pick up my calculator, I'll notice torr divided by torr cancel out because, as I have written over here, any number divided by itself or unit becomes the number 1. And now I can pick up my calculator, turn it on, make sure it's clear, and take 752 and divide it by 760. And my calculator gives me this big number, 9.8947, actually goes 36842 times 10 to the minus 1. This is 3 significant figures. These are exact numbers, 1 and 760. So I should round this off to 3 significant figures. Keep the 9, keep the 8, keep the 9. Use the 4 to round off. And is that 4 or less? Yes, it is. So I'm going to drop that. And the correct answer for this step is this. Now, next I have to find the volume. And volume, in case you forgot, let's go back to important information. You'll see the volume has to be in liters. Oh, good news. The volume was given to us in liters. So I can write volume in liters is equal to 4.56 liters. All right, R, and you'll be given R, equals 0.0821 atmospheres, liter, mole, Kelvin. And now what do we left? Temperature. And temperature has to be in Kelvin. And no, that's not ink, that's in K. And in case you forgot, first of all, here, important information, temperature in K Kelvin. Also, I give you the universal gas law constant R. Remember, R is 3 significant figures. Now, in case you forgot, this will be important information. Quiz number 3, we have Kelvin equal degrees C plus 273. Oh, that blueberry tea is good. It's from the Republic of Tea. I also have my vanilla almond, which I had earlier. All right, so we know Kelvin equal degrees C plus 273, and degrees C is 31.2 degrees C plus 273, and that's equal to 304.2 Kelvin. So now we're ready to go over to moles and put in the pressure is 9.89 times 10 to the minus 1 atmospheres. R is 0.0821 atmospheres, liter, mole. Get your magnifying glass out so you can see everything I'm writing tiny. And temperature, which we just figured out, is 3. Whoop, that. Hold on, I was thinking of another problem. Sorry about that, sports fans. All right, volume is 4.56 liter. And then R at the bottom, let me do this right, 0.0821 atmospheres, liter, mole, Kelvin. And T is 304.2 Kelvin. Now, if you notice, Kelvin will cancel out, above atmospheres cancel out, and liters cancel out. Now, what we're left with, and let me write it over here, is 1 over 1 over mole. And I'll let you do the math, but this is equal to mole. So, and that's what we're trying to find, moles of oxygen. So now I can happily pick up my calculator, clear it, put in 9.89, second key, double E. Remember, use this minus, not the other one, to get minus 1 times 4.56, divide that by 0.0821, and divide that by 304.2. And my calculator gives me the following answer. And this would be moles. Now, this is 3 significant figures, 3, 3, 4. And when you multiply or divide, you get the same number of significant figures in your answer as the number that has the fewest significant figures. In this case, got 3, 3, 3, 4. Hopefully I'll pick 3 as the lowest. We round this off to 3 significant figures. They're my 3. Use the 5 to round off. That's 5 or higher. I'm going to drop this, increase this by 1, and then we have in the balloon 1.81 times 10 to the minus 1 mole of oxygen gas. Are we done? No. If you look up here by the question mark, we're trying to get the grams of oxygen. And now we need to do step number 2. Go from moles of oxygen, which we just calculated right here, and step 2 is moles O2 to grams O2. And so we have 1.18 times 10 to the minus 1 moles of O2. We want to convert that to grams of O2. And what do? We use our good buddy, our good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're going to get rid of goes underneath. And I'll write those units in. And where do we get this relationship? 1 mole of a compound equals the molecular weight of that compound in grams. So we need to find the molecular weight of O2. And that's equal to the sum of all atomic weights meaning 2 oxygen. If you look at the periodic table, and we've done this before, oxygen to 3 significant figures is 16.0 times 2, 32.0. So 1 mole of oxygen is 32.0 grams of oxygen, meaning gas, O2. And if before I pick up my calculator, I'll say moles of oxygen divided by moles of oxygen become the number 1, cancel out, because anything divided by itself equals number 1, meaning it's gone. And I'm left with what I do want, grams of oxygen. So now I can take my calculator, I'll put in 1.81, second key, double E, minus 1 times 32, and my calculator gives me this answer. 5.792 grams O2. And if we look at this, this is 3 significant figures. This is an exact number, the 1 for 1 mole, part of definition. This is 3 significant figures. Therefore, when you multiply and divide, you should get the same number of significant figures in your answer. Tea break. No, tea break won't be in your answer, but, oh, that was awful humor. I apologize, sort of. Anyways, 3 significant figures, 3 exact number. We need to round this off to 3 significant figures, because when you multiply and divide, you get the same number of significant figures in your answer as the number with the fewest significant figures. So it's 1, 2, 3. Use the 2 to round off. That's 4 or less. And the correct answer there would be 5.79 grams of oxygen in that balloon. And that's how you get it. And I would invite you to go back and look at the video, which I'll post later today or tonight, so you can see how I did that. All right, let's continue on with gases. Wrong slide. And yesterday, I talked about Dalton's law of partial pressures. And the total pressure exerted by a mixture of a gas, is the sum of the partial pressures of a gas. And excuse me, the pressure, partial pressure, is the pressure of that gas in a mixture would exert, meaning what it would be if it were alone under the same conditions. And therefore, Dalton's law is P total, the total pressure, equals the sum of the partial pressures of each gas in the mixture. And just to remind you, in case you forgot it, important information, quiz number 3 will have the following: Dalton's law of partial pressures, and I have P total equal P1 plus P2 plus P3 plus Pn. Pn means if there was 5, it'd be P4 and P5, but there's only whatever we have in there. So now let's have fun with Dalton's law of partial pressures. All right, let me read this. A mixture of hydrogen gas, H2, and bromine gas, that's Br2, has a total pressure of 652 torr and a partial pressure of hydrogen partial pressure of 201 torr. What is the partial pressure of bromine, Br2? And I'm going to do this stepwise with you. Right here, what I'd like you to do first is, what are you being asked to find? What are you given? So why don't you just write down, what are you being asked to find and what are you given? Your turn. And don't forget, tonight from 6 to 7:15, I have my office hour on Zoom. If anybody has better suggestion for office hours, let me know, and I can always change it. Because this semester, nobody's been showing up. And I changed it to help make more people show up, not make, allow them to show up. So if there's a better time, let me know. And no, midnight would not work for Dr. White. All right. Everybody's done with the first part, so it's my turn. And the question is, what are you being asked to find? The partial pressure of bromine gas, which we write like this. And what are you given? The total pressure of this mixture. And then you're given the hydrogen partial pressure right here. Now, how do you proceed? As soon as you see anywhere in a problem, partial pressure, immediately you need to use Dalton's law of partial pressure, which is P total equal the sum of the partial pressures of the gases in the mixture. In this case, it's partial pressure hydrogen plus partial pressure of bromine, Br2. Now, I'm going to let you try first. How do you solve for this? Get it alone on one side. Your turn, then it will be mine. Isn't it nice I'm sharing today? I always share the fun, the enjoyment. How many synonyms can I come up with fun for fun? The pleasure of doing chemistry. It is fun. I hope you're having a good time. I am. And boy, does it feel like winter out there yesterday and started this morning. Notice I got my winter top on. I keep my house on the cool side, saves on energy, and I'm more comfortable. And if I get cold, I have clothing to put on a layer. And when you're done, give me a thumbs up. All I'm asking you to do is, with the letters here, solve for partial pressure bromine. Ooh, you know what I forgot to do? Bad, Dr. White. I forgot to put my question mark there. So this should be question mark PBr2. Now, if you can't figure it out how to solve for partial pressure bromine, give me a thumbs up and I'll start. All right, my turn. All right, we want to solve for the partial pressure of bromine, meaning we want it alone on one side. But notice this is an addition. Now, let me remind you, anything minus itself equals 0, meaning it's gone. So if I take here hydrogen plus partial pressure of bromine, and I subtract the partial pressure of hydrogen, it's going to be gone because anything minus itself is 0. It's gone. But whatever I do to one side of equation, I have to do to the other side. And I did. Now, partial pressure hydrogen minus partial pressure hydrogen equals 0. 0 plus the partial pressure of bromine equals the partial pressure of bromine. And that's equal to P total minus the partial pressure of hydrogen. Now, you don't have to do this, but I like to rewrite this. That's just a good habit of mine. And good habits I don't change. Sometimes bad habits I haven't been able to change. Still trying on some of them. And I now have that. And notice we took the time up here to find out from our word problem that P total is 652 torr. And P hydrogen, partial pressure hydrogen, is 201 torr. And I won't use my calculator. I'll use my brain because I know how to subtract, I hope. And this is your answer. Let me check my math again. And that's how you do it. So this is something we've done a couple of times and you should know how to do. Now I'm going to turn the switch click off. Now where Dalton's law of partial pressures comes in, a lot of times we collect gas by water displacement. And you have a tube, you bubble gas in there, it changes the volume, and you can measure the volume of a gas you make. Now, I think we're gonna do something like this, and I'll stress the term like in one of our labs. I think the airbag lab, sort of. Maybe no, we're not using water there. But anyways, again, switch is off. In order to get the pressure of that gas, the total pressure in that tube is equal to the pressure of the gas plus the pressure of water. Water vapor, anytime you have water, there's going to be some water vapor, which means water as a gas over that water. And then you can use this to solve for P gas, just like we just did in the problem before. Now, switch is still off. The moles of a gas can be calculated using the universal gas law. We just did that. And balanced chemical equations we showed from test number 1 provides molar ratios. So you can use this to do calculations when products are gases. Now, switch is still off. There's an interesting concept in chemistry called STP, and that's standard temperature and pressure. And that temperature is 273, roughly, I think 0 degrees C, and 1 atmosphere. And at STP, switch is still off, 1 mole of a gas equals 22.4 liters. Oh no, we're at the last page of this chapter. And you know what that means? It's new chapter time. Now, we've just finished chapter 11. Listen carefully. Next Tuesday, I will go through chapter 11, practice problems. Keep up. We're moving at a quicker rate now. Keep up. Do the practice problems. They will help you do well on my quizzes and the test. And essentially, we just have one more test, but there are a couple more quizzes. And I will have to look this weekend. When's a good date for the quiz on chapter 11? And be sure to do the practice problems. If you took test number 1 already, and also my first 2 quizzes, which you did take, you'll know why I call them practice problems. So it's time for a new chapter. Wow, we're really zooming along. Just think next week, will be week number 10. Wow, this semester is going quick. Time flies when you're having fun with chemistry and Dr. White. All right, let's look at this new chapter, chapter 12. Everybody see chapter 12, part 1, solutions on your screen? Thank you. And this chapter deals with solutions. And solutions are a very important part of our daily life. And what is a solution? It's a homogeneous combination of 2 or more substances in which each substance retains its own chemical identity. So if you mix 2 things together and they don't react and it's the same throughout, homogeneous means it's the same throughout, you have a solution. And there are many solutions we have in our daily life. And let's just think about a couple of solutions. Everybody breathing right now? I hope you are. And the air around us is a homogeneous mixture of mainly oxygen gas and nitrogen gas. Think about that. The air around us that you're breathing in and not letting out the air, well, you are sort of nitrogen, but the air around you is a mixture of nitrogen gas and oxygen gas, and neither are reacting. You can isolate the oxygen gas, you can isolate, let me bring my hand back into the picture. My camera's up here and I'm looking at the monitor. I'll never be a TV announcer. But anyways, I'm a chemist. Why should I worry about TV announcing? But anyways, they're separate and you can separate them. They do not react. They do not change. Now, is it homogeneous? Right here, I'm inhaling enough oxygen to keep me alive. If I walk over to by my door or out the door down in my living room or in that other right there, a bedroom, guess what? It will have the same amount of oxygen, nitrogen, and that percentage is roughly 20% oxygen, 80% nitrogen, as it is right here. It's the same throughout, homogeneous. Now, what's another solution? My tea. We can't really, well, you can't see it. I'm going to drink some. And this is a complex solution of many things. Water. Yes, I put sugar in there, so it's got sugar. And the different chemicals that come out of the tea leaves when I put the tea bag in the hot water. That's called extraction. And we don't do any extraction in this class, but in organic chemistry, you do. And that's a complex solution. What's another complex solution? Well, next time you drive by a gas station, think about it. The gasoline they sell is a very complex solution. Did I talk about gasoline beginning of semester? What's good and what's not good? I think I did. But Shell is the best gasoline. I worked in a chemical company where part of my job was to go out and talk to some of the petroleum companies like Shell, Mobil, their research people to see what kind of molecules they need for additives that the company I was with, ooh, what's that? Anyways, company I was with would sell to them. So I got to know these people and they knew their gas and their competitors, how good and bad it was. And all of them agreed, and I think today it's still the same. Shell is the best, Mobil is almost as good. And then the worst gas, and do not buy this, please don't, is BP, which used to be called Standard. And why do I say it's that bad? Well, one reason, about 4 or 5 years ago in Gary, Indiana, and Southern Illinois, or by Gary, Indiana, I guess that's called Southern, that part of Illinois, the refinery there made gas that was so bad and shipped to the local BP stations in that area that destroyed the engines of about 3,000 cars. I'm not going to buy gas from a company that destroys my car engine, even though they paid for it. It's still a lot of grief I have to go through. So, but anyways, gasoline is a very complex mixture of a lot of different chemicals. One of the main components is octane. That's why they call it octane number. And if you take organic chemistry with me here at Elgin Community College, when I teach it here, and I teach it just about every semester at Elgin Community College, you'll find out about octane, octane number, and gasoline. So that's a complex mixture. If you drink pop, remember, I'm from the Chicagoland area, and the carbonated material in a can that's non-alcoholic is called pop, not soda. And pop is, again, a complex mixture. The main components, now this gets really complex, is water, sugar, certain flavorings, and a gas too, carbon dioxide. Those are the little bubble. I like the little bubbles. Bubble, bubble, bubble. But anyways, little bubbles or big bubbles in pop. Speaking about pop, everybody see the green can here, the bottle on your screen right now? That's Verner's, and it's called ginger soda. It's a very spicy ginger ale that's highly carbonated, and I love it. I've been drinking it for decades now. Yep, decades. And I also like Dr. Pepper. And the material, the liquid in here, and you can see the bottle here, the pop, that's a homogeneous solution. It's a complex mixture of many things. Now, the best place I've found to find Verner's is Jewel. You can buy it, just about any Jewel has it. Some other stores have it, but usually, and yes, these 12 can cases right here, I've got 3 in my house. One I'm drinking out of when I'm not drinking tea, and others for emergency backup. And you should try some. Over the years, I've told students to, and they all have liked it except one. Well, you can't please everybody. So you should know a solution is a homogeneous combination of 2 or more substances which each retains its own chemical identity. And looking at the clock, I think this would be a good time to take a break. We'll come back and I'll talk about solvent and solute and come back at 9:55 and let's take a break. Come back in about 5 minutes, 9:55, and I can get up and stretch. I'll see you in about 5 minutes. Time to get started again. Welcome back. Don't forget, tonight, if you need any help, I have my office hour from 6 to 7:15 on Zoom. You have the login. It's in my syllabus, and it's also on Blackboard. You can find it. And let's get back to solutions. Remember, solutions is a mixture, like my tea, of two or more substances that are combined to make a homogeneous, that means the same throughout, mixture. Ooh, I just saw another mixture, which I'm not going to do. I have water in here. If I put salt or sugar, make it sweet, and I shake it up like this, it will dissolve and it'll be homogeneous, and that would now be a solution. Now, when we talk about solutions, there's two components or two things you should know. Does everybody see solutions contained on your screen now? Thank you, Anna. All right, now let me be subtle. And know this, every solution contains a solvent, and a solvent is the component of the solution that is present in the greatest amount. Again, if you have a solution, the component present in the greatest amount is called the solvent. Now, you also have the solute or solutes. You have more than one. And the solute, here's the solvent, here's the solute. And you should know these. I'll never ask on a test, what's a solvent, what's a solute, but I'll expect you, and I'll show you in a little while, to know how to interpret it and determine these. Now, solute is a solution component that is present in a small amount relative to the solvent. The solvent will always be the component in the greatest amount, and the solute will be the other component or components in a lesser amount. So let's figure out some interesting things, or look at something interesting. All right, so what are we being asked to find? What's the solvent and solute? And what are we given? We have 35 grams of water and 5 grams of sodium chloride, NaCl. But I think I might have told you, you ever go out to breakfast, lunch, or dinner with a bunch of chemists like me, one of us will always ask, Could you please pass the NaCl, 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 get it? Anyways, so how do you determine which is the solvent, which is the solute? Well, the solvent is the component present in the greatest amount. And I hope you all agree 35 grams is greater than 5 grams. So the solvent is water. And everything else, in this case, there's only sodium chloride, are the solutes. So for this, the solute is sodium chloride. Ooh, that was fun. Let's try another one of these. Remember, solvent is the component present in the greatest amount. The solute or solutes are all the other components. All right, let's do this stepwise. A solution contains 5 grams, G is grams, of H2O. I hope you know by now that's water, and 25 grams of ethanol. What is the solvent? What is the solute of the solution? And I'll help you out. Well, why don't you write here first? What are you being asked to find? What are you given? And then give me a thumbs up when you've done that. All right, my turn. What are you being asked to find? The solvent and solute. What are you given? 5 grams of water, 25 grams of ethanol. So once we have this, we never have to look back up there again. Now, I'm going to let you figure out which is the solvent and which is the solute. Your turn, and then I'll do it. And remember, the solvent is the component present in the greatest amount, and the solute is the component not the other ones. All right, my turn. Looks like everybody's done. So, which is the greatest amount, 5 or 25? I hope you all pick 25. So the solvent is ethanol, because that's the component present in the greatest amount. And everything else, which in this case is water, is the solute. Now, the reason I gave you this problem is in our life, in our daily world, most solutions are water. Not all, but a lot of them, where water is the solvent. But that doesn't have to be true. You can have solutions where water is a solute. So don't forget, the solvent is the component of the solution that's present in the greatest amount, and the solute is the component that's present in smaller amounts relative to the solvent. Now, we can have different types of solutions. I've already talked about this. Air is a solution. It contains oxygen, nitrogen, and actually, I forgot to talk about it, has water vapor. Now, liquid solutions, you can have pop, which I talked about. I did salt, water, ethanol, and water, and ethanol is in gasoline. Gasoline is a solution. Ethanol is a solute. And where I say ethanol water, and if you're underage, you shouldn't do this. If you don't want to, don't have to. But if you like hard liquor, Dr. White loves his vodka, and also Canadian Club, vodka is a mixture of water and ethanol, essentially. And therefore, it's homogeneous and it's a mixture. By the way, the best place to get vodka if you want to save money is at Costco. They're French, not the American. But their French stuff is, I think, really made by the same people who make Grey Goose, which is very good. I like, and Absolute vodka I love too. I love my vodka, only on the weekends. No, I'm going to have some now. No. But anyways, there are different types of solutions. Now, you can also have solids as solutions. The old, what they called mercury amalgam, which they don't really use anymore, were solids, but mixtures of different substances. Sterling silver is a solid, but a mixture of silver with other things. Now, I forgot what other things. Let's take a look. And if you see on your screen right now, I didn't know this is not an area I work in. But anyway, sterling silver contains 92.5% by weight silver and 5.7 other metals, usually copper. And what makes it, why they call it sterling? Oh, because some of the early pennies had a star on them. That's interesting. But anyways, sterling silver is an example of a solution that's a solid. And we have other examples. All right, now, important thing about solutions. One is the solubility of a solute. And I'm going to go through some definitions and click the switches on. And you should know that the solubility of a solute in a solution is the maximum amount of solute that will dissolve in a given amount of solvent. And I should also have under there, under certain conditions like temperature and pressure. So solubility of a solute, that's the maximum. You can't put one more molecule in there. You can't. Nope, 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 nope. That's the maximum. Now, let me show you something interesting on the internet. And does everybody see sodium chloride Wikipedia on your screen? Thank you. Now, I might have mentioned this before, but I can only vouch for chemistry related things in Wikipedia. The chemistry related things have been so heavily policed by chemists. I do organic chemistry, and I have the credentials. If I ask for a change, they make it. That it's been many years since I've seen any mistake in chemical stuff in Wikipedia. Now, if you look on the right-hand side, if you see I have names and then identifiers. Oh, properties. If you look down here, they have the molar mass, how many grams per mole, and they have the density. And if we go here, solubility in water. This is the maximum amount you can put in. You have pure water, which we don't, but let's assume you do. At 25 degrees Celsius, you can put in 360 grams of salt per 1,000 grams of pure water. And that's the maximum. You can't put one more molecule after that. And that tells you. And I don't know why, but they have the solubility in ammonia. And it needs clarification. The solubility in methanol, they don't have a temperature. Why people would need that, don't know. But let's look at another one. And sucrose. Sucrose is the molecule you call table sugar. And if we scroll down on the right, you'll see names, identifiers, and then properties. And here they have approximately at 25 degrees C. They have a lower table. Let's see where that lower table is. Here it is. Now they have DL. Why they do deciliter? That means 100 milliliters. And you can put in at 50 degrees C, 259 grams of sugar. That's a lot. And sugar is very soluble. Notice how as your temperature goes up, you can dissolve more. But if we go back up here, the solubility is about 200 grams of sugar in 100 milliliters or grams of water. So solubility is an important feature of a solution and a solute in that solution. And you should remember that's the maximum amount. If you're adding a solid to a liquid like water and you've reached the solubility of that solute, nothing more will dissolve. So that will just float to the bottom as what we call precipitate. There'll be a solid at the bottom. Now, what affects solubility? I'm going to turn the switch off, but you should remember what solvent you're putting it in, what the temperature, what is the solute. As you just saw, salt is less soluble in water than sugar. because they're both in the same solvent. Now, sometimes something that will affect solubility, are there other solutes already in that solution? And sometimes even the pressure that solution is under. You have pop, when it's at atmospheric pressure, there's a lot less CO2, carbon dioxide, in the liquid than when it's under high pressure before you open the bottle or can. So these are all factors that affect solubility, and solubility of a solute is the maximum amount of solute that will dissolve in a given solvent. Now, there are different types of solutions. I'm going to be subtle. And you should be familiar with the types of solution. And notice, hint, know these. All right, the first one I like to talk about is a saturated solution. Now, saturated solution is a solution that contains the maximum amount of solute that can be dissolved under the conditions in which it exists. You can't put one more molecule in there. If you did and tried, it would just, if it's a solid, go to the bottom. And a saturated solution means you've got the maximum amount of solute. And when I worked in a lab, an organic chemical lab, we would make up certain saturated solutions that we would use. They're very useful. So a saturated solution, you have the maximum amount of solute that can be dissolved under the conditions at which the solution exists. Now, we have what's also known, you should know, a dilute solution. And a dilute solution contains a small amount of solute relative to the amount that could dissolve. Again, a dilute solution is a solution that contains a small amount of solute relative to the amount that could dissolve. And what do we mean by that? In my water, let's assume I have 100 grams, and let's assume the solubility of, I don't know, let's do sugar, 250 grams. If I only put 1 or 2 grams instead of all 250 that could fit in here, that would be a dilute solution. A dilute solution where you dissolve only a small, tiny, I'll look up here in the camera. Oh, he's practicing being a TV announcer. A tiny amount of the solute that could dissolve. Now, that's called a dilute solution. Now, here's a Dr. White story. A long time ago, I was in this bar, and some bars that are a little shady, like a lot shady, when you get a mixed drink, they dilute it a lot, so there's not much alcohol in there, so they can make more money. Now, I was in this one bar with some friends, and the bartender brought my drink, my friend's drink. I drank it, and it's something I'd ordered before, often at other bars. There's not that much alcohol in there. I called him over and said, you know, this is a really dilute drink. And he did not like being taught chemistry and what dilute, he knew what dilute meant. And we never went back to that bar again. We left pretty soon after that and found a better place that didn't dilute. Serve dilute drinks. So remember, dilute means there's just a tiny amount of solute present in the amount that you could dissolve in that solution. All right, now another type of solution that you should know is called a concentrated solution. And a concentrated solution contains a large amount of solute relative to the amount that could dissolve. So if I have my bottle of water and I can put in 250 grams of sugar to dissolve in this water, let's assume I could. And if I put in 200 grams, not enough to make a saturated solution or a saturated solution, but since I have 200 grams, which is pretty close to what you could, the total amount that could dissolve, this would be called a concentrated solution. Now, the term concentrated solution has been shortened and is in our daily life. Really? Yes. Well, it's sort of fallen out of favor compared to what it used to be. When I was in high school and college, they didn't have what you now mainly buy in a supermarket. And does everybody see on their screen the Minute Maid? I don't get any kickbacks from them, or Old Orchard frozen orange premium juice. And what they call this, and you can see here, concentrate. And what do they mean by concentrate? Well, normal orange juice has certain chemicals along with water in them. And if you take out a lot of the water, the amount of other chemicals level goes very high. And therefore, that's a concentrated solution. Now, marketing people, instead of saying frozen concentrated solution, to shorten the words to say concentrate. But mostly now you buy normal solution of orange juice. It's already got the water in there in the bottles. But until, I don't know, that's a pretty new thing. In the last only 20, 30 years that became popular. Yes, I'm older than that. Most of you aren't, but back when I was in high school and college, they didn't have the orange juice you now buy in the supermarket in the bottles. You bought concentrate. Now, so another Dr. White story. I almost forgot. When I was in college, I was in a fraternity, Alpha Epsilon Pi. It was a fun time. Wow, fun time. No, I'm not going to tell you about our toga parties. But anyways, we had one of my fraternity brothers. We all had nicknames, and I'm not going to tell you mine. But his nickname was the Beast, like from X-Men, because he sort of looked like that character. But anyways, the Beast, and I can't remember his real name right now. It's been so long ago. I'm still close to some of them, but I think he moved out of state. So, but anyways, one of the favorite things he loved was to eat orange juice concentrate right from the can. I must have, but anyways, he would love to eat that. You like that? Yeah, you want some? No, thank you. But it was a concentrate, a very high amount of the different chemicals or flavors and taste and sugar too, that's in orange juice, where they take some of the water out and increase the level. And that's called a concentrate because that's truly a concentrated solution. That's a salad too. I can still remember seeing him sitting with a can like that, frozen, and eating it with a spoon. Oh, we had some wild and crazy guys in my fraternity. We had a good time too. So you can have a concentrated solution. Now, probably the most important one, thank you, Anna, I can talk about is an aqueous solution. And you should really know this. Hold on. Don't you love it when I'm subtle? And know this. And what's an aqueous solution? That's the solution in which the solvent is water. Water being the solvent, that means in that solution, water is the component present in the greatest amount. So, one other important thing, you show something as an aqueous solution by bracket. Hold on, let me change colors. When you have, and I'll teach you later where this applies, A, Q, close bracket. And that means you have an aqueous solution. An aqueous solution is a solution in which the water is the solvent. If you think about it, any pop you have, water is the greatest component, meaning the solvent. So if I have a can of pop or bottle of pop, like Verner's or Dr. Pepper, Dr. White, like I'm a Dr. Pepper too, even though I'm a Dr. White. Let me think about that. It gets confusing, but I'm a both. But anyways, I love my Dr. Pepper too, along with Verner's, and both of those. And for those of you, and I don't like Coca-Cola or Pepsi, I never really was into cola pops. Yeah. But anyways, I don't like coffee either. Yeah. But if you like pop, that is an aqueous solution. So the next time you're out with friends and you see them drinking some pop, you can tell them, you know, you're drinking an aqueous solution. That means the solvent is water. Don't. Friends don't like to be taught chemistry when you're out partying with them or going out to dinner. Nope, 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 nope. But you should know. It even says it on the screen. Know this. Aqueous solution is a solution which the water is the solvent, and it's shown in a formula, which I'll teach you later in this chapter, bracket AQ, close bracket. And aqueous comes from the Latin, also Spanish term, aqua, which is for water. Now, I won't ask this, but there's another type of solution, and that's called non-aqueous. Non means the prefix not, and non-aqueous is a solution in which a substance other than water is the solvent. And you better hope the gasoline you buy is non-aqueous, which a lot of people infer means there's no water present. And you do not want gasoline to have water in it because it will freeze up in your engine, do some very bad things. So non-aqueous water is not the solvent. Usually it also means nowadays there's no water present. Now, let's think about the following. I have my water here, my fancy container. Yes, I refill these. But anyways, I got water in here. And if I had some salt or sugar, both are solids, and I put it in there, and I go like this to shake it up, and all of a sudden, it's gone. No, it's what we call dissolve, to make now a solution, either water and salt or water and sugar. And what's happening? What happens when you put the solid into the liquid to make a solution? Good question. Thank you. You're welcome. Well, what happens is there are different interparticle interactions. Now, the prefix inter means between two separate particles. If you ever go to O'Hare and you want to go to another country, you go to the international area departure gates. What is international? Different outside nations. You're going elsewhere. I don't know if I told you back in the, for many decades, I worked for two Dutch companies, Anglo-Dutch, mainly in the Netherlands. And often I used at least 4 or 5 times a year. I'd be there for a couple of weeks at a time, 2 to 4 weeks. I would go to Europe, mainly the Netherlands, and I'd take an international flight from O'Hare Airport to Schiphol. Schiphol, by the way, is the Dutch airport in Amsterdam. I don't know if I told you this. You know what it means if you're not having a good time in Amsterdam? You're dead. It's a great city. I mean, wild city, fun city, also very cultural city. Another great city is Guadalajara in Mexico. That's a wild city too. But anyways, let's get back to when you put the sugar into water, what happens? Now, there are different interactions already present. The solute is a solid because between the two particles, there are interactions holding together as a solid. And the solvent, the water, notice they're not water molecules floating all around. They're all together. And they're interactions holding the water molecules together. And when you mix two together, you have to break those interactions to form new ones between the water and the sugar molecules. And that's what happens when you form a solution. So the next time you put some sugar in your tea, you're forming a new solution and you're doing all those different interactions between the different molecules that you're mixing, like sugar and water. Or if you're doing other types of solutions you're making those types of situations. Like if you're going to go cook some noodles or rice and you put some salt in the water to salt it first so it tastes good, you're doing that too. I bet you never thought all the different ways chemistry is in your daily life. That's why to this day, when somebody I hear say, I hate chemistry, I laugh inside because, come on, chemistry is everything around us, keeping us alive. The air is chemistry, solutions is chemistry, and we'll get into a lot more stuff this semester that's chemistry. If you take organic chemistry, my skin, my hair is chemistry, the metal here, my phones, everything it's made of, everything you see is chemistry except for light. That's, I think, physics. But there are parts of chemistry that deal with that too. Now, what are factors that affect solution formation? Again, switches off. Now, if you're trying to dissolve something, the state of the subdivision of the solute, if you have a powder real fine, like sugar, and you put it into water, it's going to dissolve quicker than if you have big hunks of sugar, all solid, like rock sugar, rock candy. Well, that's something I haven't had in decades and don't need. Rock candy, which is sugar as a solid, big crystals. Hold on. Everybody see the big crystals of rock candy on your screen now? That's going to take a lot longer to dissolve than if you have the fine solid powder that you buy at the supermarket in the bag. That's why it's fine and very small, not coarse like this, big hunks. because it allows you to cook quicker or dissolve it into whatever you're going to do. Oh, by the way, years ago, I broke a tooth on rock candy, and that was the last time after cracking a tooth I ever had rock candy. No, I don't want to go through that again. It's good stuff, but no, I don't want to pay that money and go through that pain of a cracked tooth. Oh, it hurt. All right, now another thing that will affect how fast you can form a solution is the agitation. And notice when I said put some in here, shake it up, that's agitating it, or mix it. The quicker, the more harder you mix it, the easier the rate, the faster the rate of solution formation. And finally, temperature of the solution components. If you've ever made a syrup solution, which is a lot of sugar and water, a lot, to do it quicker, you put it in a pot, heat up the water with the sugar, start mixing, that's the agitation, but the heat from the flame, or if you have electric stove, the heat from the coils, I like that, coils, flames, those will affect how fast that solute dissolves in the solvent, in this case, sugar and water. And when you heat it up, it goes quicker. Same thing with salt. You know something? I'm going to do something that I think would be a good thing. Instead of rush throughing the next thing called solubility, I'm going to let you out a couple minutes early. We're ahead of schedule. We're actually right on schedule in the syllabus. So with that, I'm going to end a little early. Don't tell the dean. Actually, you can tell the dean because for a net course, I'm not required to lecture like this. I have it set up and say, meet with my students 2 hours a week, like my office hours, but I don't think that's fair to you. That's why I do actual lectures and post it on Zoom. But I think this would be a good time to take a break. And I'll say, don't forget, if you haven't already, take test number 1 today or tomorrow. Today is Wednesday. I'm looking up at a calendar I have up there. The 19th of October, or tomorrow, Thursday, the 20th October. By the end of tomorrow, you should have to, you don't have to unless you want a 0. You should take test number 1. Don't forget to ask for a periodic table if they don't give it to you. And also make sure they print it one side only. I've asked them to do that. And with that, I'll also remind you, if you have any questions about anything, feel free to come to my office hours. I have it on Monday, Tuesday and Wednesday. And today being Wednesday, tonight at 6 to 7:15, I'll have my office hour. And with that, we're done for the week. Don't forget, if you have Dr. White withdrawal symptoms, you can always go to my YouTube channel and binge watch me. With that, I'll say, gang gesund, goodbye. I'll see you either tonight, my office hour, or next Monday. One last thing, don't forget, I'll go through the test on Monday.